going to get started. It's a pleasure for me to introduce my student, soon to graduate, Daniel Elton, who's been working in the group now for about 4 years. And
3.5.
And he's been doing really extraordinary work. And as the proof, this paper was very recently published in Nature Communications. And there, I have to say that all the credit goes to Dan, because this is really his work. I just supervise him, but I have to say he's one of those students from which I think I'm learning more from him than he's learning from me. So this is a really nice story, and I hope you end up having a nice picture of why water is such an interesting and surprising substance and material. So.
All right. Well, I'm mainly going to be discussing the work that we recently published on propagating optical phonon-like modes. So we study liquid water, and you might think we know everything about water, but water is extremely complicated material. And over 73 anomalous properties have been tabulated. The most well-known of those is that the solid form of water is less dense than the liquid form. And most of those anomalies can be related to the presence of hydrogen bonding. And water contains a hydrogen bond network, which is a fully connected network that extends through all of space. And it's in a constant kind of state of flux as hydrogen bonds are broken and reformed and molecules transition. And there's an ongoing debate about the structure of water, meaning like how close is the structure of the hydrogen bond network to what you find in ice, and also whether there are inhomogeneities in the structure, like over nanometers scales, and also how the structure changes with temperature, going from supercooled to superheated water. So most of the work I did was with classical force field molecular dynamics, because with classical force fields we can probe a lot longer timescales and larger system sizes than ab initio techniques. And we find it useful to compare like 3 different types of models. You have the rigid models, where the geometry of the molecule is fixed. Then we have a flexible model, and then we have an ab initio based flexible and polarizable model. And so for the people here who are not physics majors, it's important that I discuss phonons and the different types of phonons. A phonon is the quantum mechanical unit of lattice vibration. So just like photons are the discrete units of electromagnetic waves or vibrations of the electromagnetic field, phonons are the discrete units of lattice vibration. And they're optical phonons, and then they're acoustic phonons. And phonons can also be longitudinal or transverse. In the longitudinal phonon, the atoms move along the direction of propagation. In the transverse phonon, the atoms move perpendicular to the direction of propagation, which is denoted by the vector k. In the optical phonon, the blue and red atoms can be thought of, pictured here as atoms with opposite charges. And in the optical phonons, the opposite charges move out of phase with each other. Whereas in the acoustic phonon, the opposite charges move in phase. And the consequence of that is that electromagnetic waves cannot interact with the acoustic phonons. But they can interact with the optical phonons. So in my work, we focus on the dielectric susceptibility, which describes how the material interacts with electromagnetic waves. So we only study optical phonons in our work. So then I need to explain what dielectric susceptibility is. Dielectric susceptibility can be written as a function of frequency here, and it relates the polarization that, of the material to the applied electric field. And normally we think of susceptibility as being local, which means like if you apply an electric field in a small region, the polarization response is also in that region. But when you have correlations in the material, then you can get a non-local response, which means that the polarization response at a point R, it depends not just on the electric field at that point, but also at the electric field of surrounding points. So that's why you integrate here over the electric field at different points, R prime. Because of convention, you use the electric displacement, but you can think of that as an electric field. And when you Fourier transform this, you get a wavelength dependence in the susceptibility. Normally, we don't think about wavelength dependence because when you're probing with light, the wavelength is 800 nanometers, and it's much larger than the size of the molecules. So it normally doesn't matter, but we're interested in wavelength dependence or Kdependence, because that's where you can see the signatures of propagating phonons.
Wouldn't non-local response be chi of R comma R prime?
Oh, yeah, in general it is, but here we assume that the medium is homogeneous. Yeah. So, and we calculate these things with the Kubo formula, which relates the susceptibility to the fluctuation of the polarization in the equilibrium state. So this is what K-dependent susceptibility looks like for water. You have three regions of interest corresponding to the librational motions, the HOH bending, and the symmetric and antisymmetric stretching motions. And the important thing here is that in the longitudinal susceptibility, especially, you see that the peak shifts a lot with K. And right, that shifting of the peak is called dispersion, and that's a signature of a propagating mode.
What is a libration?
Libration is it's a hindered rotation. So it's like a small angle oscillation. yeah, the restoring force would be through interactions with other molecules.
So I guess I'm wondering what this experiment, how you do this experiment, I guess.
Mhm.
Omega is the frequency. What's the knob that you use to
K.
tune K experimentally?
Well, experimentally, it's actually not possible to measure to make these kind of plots, because you can't arbitrarily change. K and omega are not independent, right?
So
You can't arbitrarily pick K vector at certain frequency experimentally. Yeah. So, well, you can get these susceptibilities at K equals 0. And in fact, I'll show you that in a minute. Mhm. Yeah. The other limit where you can get this is in the limit that frequency goes to 0. Then you can get this from X-ray scattering, where you can pick K and you can get to these small K values, which are very
So it,
or this type of K range. Yeah.
so at K equals 0 and omega equals 0, how close are you to recovering the dielectric constant?
Well, with this model, which is TTM3F, we get a dielectric constant around, which is a little overestimated. I think it's like 90 or something. Experimentally, it's 80. That would be in the transverse. You can read the dielectric constant off if you go to low K, small K, limit of small K, and omega goes to 0 here. So that'd be way. So from what we can do is we can fit peaks like Lorentzian type peaks or to the spectra at different K, and then we can obtain dispersion relations. And these these labels are actually flipped. I don't know how that happened. But that's actually really bad. But the longitudinal and transverse labels are flipped. So, but in the longitudinal case, you see a lot of dispersion, and transverse case, there's less. This is basically looks exactly like what you expect optical phonon modes to look like. And the way you can tie this to experiment is like I said, at K equals 0, you can get the longitudinal and transverse susceptibility. And there's you can see a splitting between the longitudinal and transverse peaks, which is called the LOTO splitting. And that's very important because LOTO splitting indicates that you have long-range sort of that you have the generation of a macroscopic electric field in your system. So it's considered to be due to long-range correlations and motions in the material. And the degree of LOTO splitting can be related to the underlying structure. So like in a crystal, the LOTO splitting is related to the structure through this equation, where C depends on the crystal structure and V is volume per unit cell. And also, the LOTO splitting in water is reproduced in ice with about the same degree of splitting. So, yeah, this means that the phonons that we observe in water are very likely similar to the phonons in ice. And recently there was some research on ice 11, which has basically the same structure as regular ice, but the hydrogens are ordered. And they found in the librational part of the spectrum there are propagating phonon modes. And so the modes consist of coupled motions, which they call wagging and rocking. And some of these modes exhibit LOTO splitting with about the same degree as in what we find. Question?
Actually, I got confused. So the electromagnetic response is generally coupled to charged radiations. So phonons are like chargeless. When you load them with heat transfer.
Mm-hmm.
Confused how these two things are intertwined.
Well, I haven't talked about heat transport yet.
What I'm saying is that how the polarization slide is
Mm-hmm.
to the conclusions about phonons.
Yeah. Well, the signature of the phonon is the dispersion. That's how we identified these the peaks as being due to phonons, is by looking at Kdependence and seeing the dispersion. So we hypothesized that the librational phonon-like modes we observed in water are similar to these ones in ice. And from the dispersion relation, we can get a velocity of propagation, and then we know the lifetime is you can get from the sort of width of the peak. So with velocity and lifetime, you can estimate the range of propagation. And for a longitudinal mode, it's about 1 nanometer. We wanted to verify that the modes are actually propagating and quantify the range of propagation. So I'll come back. So we broke the spectra into components that depend on the correlation of, basically depend on the length scale of correlations. So, which is, we call R. And so when R equals 0, you're just considering polarization fluctuations from the single molecules, and you're ignoring all the correlations between the molecules. So in that case, in librational region, you get 2 peaks, which correspond to the two librational modes of wagging and rocking. Then when you start to increase R, you start taking into account the correlations of molecules in a sphere of radius r around each molecule. So what you see is that as r increases, this peak is suppressed. That is due to anti-correlations at that frequency. And meanwhile, this peak here is enhanced. And what's interesting is that the effects of correlation and anti-correlation contribute up to fairly large distances of about 2 nanometers. And that's in a 4 nanometer size simulation.
So how's R different from K? Because when I'm thinking about, okay, I'm a single molecule and I'm just like bouncing by myself, but I'm not interacting with them. I'm thinking of like, I guess it would be K.
Well, Kdependence also tells you something about the correlation of molecules at different distances. So there is sort of an analogy between the two, but here we decide to pick a particular K. So here we chose the smallest K we had available, which is 0.15 inverse angstroms. And then ask at that wavelength, how do molecules at different distances contribute?
So that's basically partitioning the sum of the formula that you have.
Exactly, yeah. Yeah. It's limiting the sum, yeah. And then what I skipped over was this slide, which shows our work leads to a reinterpretation of the Raman spectra. Because in the Raman spectra, in the librational region, it's normally fit with 3 peaks. And these peaks were sort of naively assigned to the 3 possible librational motions: twisting, rocking, and wagging. But there's a problem with this assignment, which is that the twisting motion, which is the lowest frequency motion, should not show up in the transverse dielectric function because it doesn't change the dipole moment. It's just a rotation around the dipole moment axis. So but you actually do see a peak at exactly the same frequency in transverse dielectric function and infrared spectrum. In our work, we interpret this peak as a transverse optical phonon-like mode, and we interpret the highest frequency peak as a longitudinal optical phonon-like mode. And that explains why the highest frequency peak shows up very strongly in the longitudinal dielectric function, but doesn't show up in the transverse dielectric function. Okay. So in conclusion, the dynamics of water seem to be closer to ice than previously thought. And we reassigned the vibrational stretching peaks to optical phonon-like modes. They have lifetimes of 0.1 to 0.5 picoseconds, propagation distances of up to 2 nanometers, and they exhibit LOTO splitting, which can be a novel probe of structure. Okay. And I had some more material, but I think I'm out of time at this point. Yeah, question.
So I guess jump back 1 or 2 slides. I guess it's onto
Yes.
there we go. So you had that nice interpretation of length scale of correlation. So can you basically, for each of those peaks, say what length scale is important? I mean, can I think of the Raman spectrum?
Mm-hmm.
What's the length scale in which I have to understand what's going on in order to understand Raman?
Well, yeah, previously people thought that the dynamics occurred like in clusters. So people looked at spectra of gas phase clusters, and when you get up to a cluster with about 5 molecules, or you start to reproduce the spectra of the bulk. So people thought dynamics are limited to small clusters. But what we're saying here is that they're actually propagating modes which can travel over fairly large distances. 2 nanometers may not sound like a large distance, but there are hundreds, perhaps even 1,000 molecules in a sphere of radius 2 nanometer. And we can say, like, very concretely, this is a optical phonon-like mode, and this is an optical phonon mode. And then here in the middle, we find there is a response from the single molecule motions. So the single molecule libration motions are also contributing in between. Yeah.
Just to make sure I understand, the red here is an experimental result on top of your.
Any other questions?
So those are
Now, this is not showing the actual fits here, but these are fits that I did myself.
So I guess the question is, the red is experiment, and the green is a fit to the experiment.
Mm-hmm.
So that those are the simulations.
Right. Yeah. Yeah, the green lines are just fitting peaks.
But can you
So it's a
convolute
little-
the results from theory along the same lines?
You can, yeah, you can fit peaks to this
Right.
to this data. I have more.
Supposedly the
Mm-hmm.
same curves?
Sorry, what?
Are those supposedly the same curves, like I think Robert was asking.
Here.
If you did
Yeah.
theory on top of experiment.
I also have I have a plot showing that in our paper. Yeah, I mean, I can pull it up if you want to see it. Yeah. But
But the models don't exactly reproduce the location of the peaks on the experiment.
Right.
It's not exactly the same location, but yeah.
in our paper, we have that here.
It's pretty damn good, though.
Yeah, that was.
So the
Yeah, comparison.
I mean, I have to say that one of the best things that Dan did, which is amazing that nobody had done before, is the experimental curve, the separation into two longitudinal and transversal.
Yeah.
That actually hadn't been done. So he actually went and looked for experimental data and then separated.
Mm-hmm.
There wasn't, the experiments were there, but now I have to.
Okay, so D has these.
It's enhanced here. They're not divergences. It's just they're very sharp peaks.
Yeah, so which,
It seems
which,
that-
which the models
yeah.
is which the tip.
TIP4P is the flexible model, and TTM3F is the polarizable one.
Okay.
Yeah, well, it's actually very interesting that there's these sharp peaks. It seems to indicate that there's actually too much polarizability in the model.
So the A is just pure
it-
classical, right? Classical
force field.
Yeah, both of these are considered classical force fields, but B is parameterized from like ab initio
Okay.
things, and it has polarizability in it. Yeah. And then the other interesting thing is here in the stretching band, the flexible model does not show any LOTO splitting. And the reason for that is that in order to have the propagation or correlations that extend through space, you need to have the polarization. There's other work that showed basically the same exact result. That when you have polarization in the model, it allows for large length scale correlations at the OH stretch frequency. Maybe, I don't know.
What about some of the computational details? I mean,
Mhm.
code we're using, how long did it run?
Yeah. Well, I have more for people who are interested in computation. Like I have another part of the talk where I talk about my current work. Do you want me to go into that?
Possibility is
Okay. It was more.
just briefly.
Yeah.
But we are in the Institute for Computational Science, so it's all close.
Yeah. Well, what I did previously was using what's called the GROMACS code,
Cool.
which is,
Thanks.
and for TTM3F I use my own MD code. What I'm doing, because there was no package that supported it. So the code for the force calculation was available, but I had to write my own MD code to do the MD. But what I'm doing now is called path integral molecular dynamics. And the idea is you want to simulate water from the ab initio level, starting with the basic laws of physics. And normally you assume you use the Born-Oppenheimer approximation, and part of that assumes that the nuclei can be treated classically. But in water, the hydrogen, because it's very light, is actually very quantum mechanical in nature. And that leads to important effects like redshifting and broadening of the OH stretch band. The delocalization of the hydrogen causes a weakening of the OH bond, and it correspondingly strengthens the hydrogen bond. And so I wrote a code which does the path integral calculation. Basically, in the theory of behind it says that there's an isomorphism between the quantum mechanical partition function and a classical system of which looks like this. So you can simulate the corresponding classical system and then get the quantum mechanical properties out of it. And what the isomorphism says that for each atom, it gets mapped onto a ring polymer, which is a collection of pseudo-atoms or beads, which are connected by harmonic springs. So, and each bead interacts with a bead on the corresponding, interacts with a corresponding bead on the other atoms. So this And as n goes to, the number of beats goes to infinity, that exactly reproduces the equilibrium quantum mechanics. But normally you truncate around 32 beads. And the cost of calculation will be multiplied by the number of beads, or 32. But what's interesting is it can be parallelized very easily. And in my code, I did parallelize it over the beads. But doing the force calculation is very expensive because you have to do the DFT. And that requires a lot of processors itself. So to do this, you have to, with DFT, you have to use a lot of nodes. And the communication between the nodes is very slow. So it's basically impossible with current computer hardware. But when developing functionals, we think it's important to include the nuclear quantum effects. So that's why we're working on a way of doing that much more efficiently. Yeah. Just empirically, like from my own experience, as soon as you parallelize between nodes, there's no speed up.
Is it used hardware or the asset is where mainly intelligent? So we have to do lots of register analyzations which are not sparse
Yeah.
either ends. So it's basically scale attack what it's doing.
There's a couple like different problems. One is the DFT calculation cannot scale beyond one node because of what she just said. And then the other problem is even with the. Mm-hmm.
But the basic limitation is how a scale attack scales. It really scales up to 64 colors stars and stars to scale. So that's what the scale. Well, each simulation, let's say, you do this calculation of these 64 cores in the circuit. And ideally, it should scale better, but you just don't do the effort of doing the diagonalization.
This is in the DFT.
This is in. But yeah, so here you have to do the DFT calculation in parallel, but then you also have to do you have to do 32 DFT calculations also in parallel. And
Did you run most of the calculations?
here on for this, I've been doing it on LI Red here. Mm-hmm. So I'm happy. Mm-hmm. Yeah. So, yeah. So for those who are interested, I'm happy to discuss the work I'm doing with the IND.
And congrats on the paper. That's a great job to get into.
Thanks. All right.